like we're here first. All right, welcome back. Good morning, all that usual jazz. I don't have my math lab pulled up at the moment, so the due dates are same as last time that we've discussed. No surprises there. I want to say 1.6 is due this Wednesday the 30th. 1.5 is probably already due. And we will be finishing 1.7 today, so that'll be due in a week, which I have already set up that homework due date, which is, what is that, October 3rd? I'm still here. Sorry, I'm making sure. No, October 5th. I was way off. October 5th. And then I said the first test is likely to be around the October 7th. Now, I don't actually mean exactly on October 7th. If you remember, I said I was going to give you a 2-day window. So it'll either be the 6th and the 7th or the 7th and the 8th. I have not made that decision yet. I will let you know. You'll be getting review materials, blah, blah, blah. So yeah, we will come back to that when it's a little more relevant. But for now, let's continue where we left off in 1.7 with a super quick just rediscussion of everything we've seen. We said that interval notation is going to be something that is going to be seen throughout the semester. You're never going to get rid of it. You've got to put up with it all semester. If you don't learn it now, that was my knuckles popping, by the way. If you don't learn it now, then it's going to be a problem in chapter 2. It's going to be a problem in chapter 3. It's going to be a problem in chapter 4. So remember the difference of brackets and parentheses. Remember that it's always the furthest left, comma, furthest right. Infinities always get parentheses. Remember, any infinity that goes on the left is a negative infinity. That's very, very important as well, because if you wrote this right here in my math lab, but you miss this, the whole thing is wrong, and that's going to frustrate you to no end. So please make sure you're getting all the little details correct. We talked about the idea of a union for when your answer has 2 different windows. So something like x is less than 12 and x is bigger than 50, like this example. So you have interval notation for both of those shaded regions, but this union symbol is basically saying, hey, it could be from the left set or it could be from the right set. So the union is a symbol we'll see pretty regularly throughout this course. Intersections, not nearly as much, maybe once or twice throughout the rest of the semester, but this is still an important mathematical idea that you'll be using in calculus, differential equations, statistics, all sorts of other things. So a union is saying all of the regions that you have shaded are the solution, whereas an intersection says it's only the overlapping regions that would be a solution. So in particular, if I wanted to know what is the intersection of this, it would be nothing. It would be empty because those 2 shaded regions don't overlap at all. So you can have intersections that are the empty set, the null set, nothing. Yeah. And then we did some examples with that. Then we actually got into solving linear inequalities, which we said all the rules for adding and all the rules for equations are the same as with inequalities, except you should always move your variable to the left just to make things a little easier. And I described how you can move it to the right, but it might mess up your inequality or your interval notation or your graph. And that if you ever multiply or divide both sides by negative, to flip, which means reverse the direction of the inequality sign. And then something that'll be relevant when we get to later problems, not necessarily in these sets, but once we get to the absolute value stuff. When we get to compound inequalities, which is kind of like this one right here with the -3 and the 10. It's not just whatever you do to one side, you do to the other. It's whatever you do to one side, you do to all 3 sides. Now, I didn't specify 3, but there's 3 sides, so it has to be all 3 sides. No, there is not a 4-sided compound inequality. We won't be dealing with anything like that, so don't sweat it. We did one simpler example, and now we're going to do one with fractions. All right, so that greater than or equals just a touch ugly. Let's make it a little prettier. There we go. 3x over 5 plus 2 is greater than or equal to x over 3 plus 1. So we're going to solve this. We're then going to graph it on a number line, and we're going to put this in interval notation. Now, as I said, homework and tests, you're not always doing both of these aspects. Quite often, you're just doing the interval notation, but it might actually benefit you to graph it pencil paper anyways, because getting the interval notation is much easier when you're looking at the graph versus looking at the inequality form. All right, so why is this one more difficult? Because you got fractions. You got denominators of 5 and 3. Well, we treat equations just like inequalities, and we said, hey, we can identify an LCD, which for this problem between 5 and 3 would be 15. And then we multiply every single piece by the 15. 15 times the 3x over the 5, and then 15 times the 2, and 15 times the x over 3, and then 15 times the 1. So I'm just going to fill everything else out. 3x over 5 plus 15 times the 2 greater than or equal to 15 times the x over 3 plus 15 times the 1. I didn't just multiply it by the parts that have fractions. Even the parts that were whole got the 15. I'm not multiplying the 15 into the bottoms. These are multiplying into the tops. These count as 15 over 1 if you really need to be methodical and do it that way. It's up to you. You can divide and then multiply, or multiply and then divide for each of the fraction situations. I've said before it's easiest to divide first. So I'm going to say 5 will go into 15 3 times, and then this 3 times this 3 would be 9. So that's what I'm doing, although I'm going to unshow that. So again, the 5 and the 15 reduce to a 3 in the top. Then that 3, the blue 3 times the black 3 would give us a 9, and the x we're still stuck with. So that's now going to be 9x after reducing it. Again, 5 goes into 15 3 times. 3 times 3 is 9. Plus, the 15 times the 2 is just 30, no reductions, greater than or equal to. I did not multiply both sides by negative, so no flipping. For this one, 3 will go into 15 5 times, and then that's just 5 times x, which will be 5x. And then plus, I think I accidentally erased the 1 I had here from hitting undo too many times, but then the 15 times the 1 gives us a 15. No more fractions. That's our happy place. With no more fractions in an equation or an inequality, it makes it a lot easier. So now what we're going to do is, no matter what, let's move the variables to the left just to make this as simple as possible. So subtract 5x on both sides. If we're subtracting 5x on both sides, that means the constant's got to go right, so we're going to subtract 30 on both sides. All right, the 9x minus the 5x is going to give us a 4x. The 30s will cancel. We bring down the greater than or equal to, the 5x's cancel. 15 minus 30 is negative 30. Remember, you should be able to do that without a calculator. All right, only one final step left to solve, and this is 4 times x, so we have to divide both sides. Divide both sides by 4. Now, I'm going to write something to the side, flip question mark, because a lot of people, at least the first or second time they do a problem like this, will flip this. Because they say, oh, well, I saw a negative, so you flip it. No, it's not because you saw a negative that you flip it. It's because you chose to multiply or divide both sides by a negative. So yes, there's a negative there, but that has nothing to do with the flipping. There is no negative in front of this 4, which means we did not need to divide both sides by a negative. So no, we in fact are not flipping this. We will leave it alone. So it's just an x on the left. We leave the greater than or equals to, and the negative 30 over 4 is going to reduce to negative 15. You know what, I said a number earlier. Sorry about this. I said that 15 minus 30 was negative 15, and then I was looking at this minus 30, and I wrote minus 30. It's like something looks wrong here. So this was supposed to be a 15. This is the number I just corrected. Sorry about that. This format of teaching has me make those silly mistakes twice as much as usual. I'm sorry. I blame not being able to look at what I'm writing at. Okay, so again, please get that 15 minus 30 was negative 15. Once again, I apologize for that mistake, but I'm glad I caught it. So 15 and 4 does not reduce. This will just be a negative 15 over 4. So again, it's not just because there's a negative somewhere that you're going and flipping things. It's if there's a negative paired with the x, because then you'll have to divide it out, and that's when you would have flipped this. But again, not in this instance. So there's our answer in inequality form. X is every number bigger than or equal to negative 15 fourths. The graph, we just draw a number line, We put that single number up there when we're doing this by hand, negative 15 over 4. Greater than with the x on the left means we shade to the right. So shade, 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 forever and ever and ever. Arrow on the right side to signify that. Because that's an or equals, that means we put a bracket, not a parentheses, on the endpoint and facing the shaded region. And then the interval notation always goes furthest left. So here's the furthest left, which is at negative 15 fourths. So we go negative 15 over 4, comma. And then the furthest right, well, we're shading right forever, so that's to positive infinity. Infinities always get parentheses. There's a bracket here because of the or equals, so there's still a bracket there. There we are. So I'm not going to do a whole bunch of these because it is really very much just like solving equations. And honestly, this is supposed to be prereq knowledge. I would say 2/3 of anything in chapter 1 is prereq material, which is why we haven't done a ton of examples. We don't really just stretch this out too much. I'm stretching out more than I feel like I should even still. So move everything, move all your x's to the left no matter what with these, unless it's a compound inequality, which we'll see later, sooner than later. Understand your interval notation, get it right every single time. One detail that's wrong it means the whole thing is wrong. This is an important notation, so there's not really any partial credit with that kind of thing. Fractions, same idea. If these were decimals, you'd multiply both sides by 10 or 100 or 1,000, whatever would get rid of all the decimal places until you have your nice whole numbers that are much easier to deal with, or integers. Integers are just positive and negative whole numbers, if you weren't sure. So I'm only going to do 2 more examples of these, and they're going to be very unique. So that was B, correct? Yes. So this will be C. And this is going to be 3x is less than 3x plus 2. Now, I don't remember seeing any examples like C and D in the homework, which kind of annoys me because they really should be. Before we changed additions, these problems were in the homework, and I don't know why it was whoever created the departmental homework decided not to put them in, and I'm not supposed to add problems, so I can't, but there really should be problems like C and D that we're about to do. So please understand, this is a pre-calc level problem, even though you might not see any in the homework. Understand it. I could still throw it on the test because it's part of the material. All right, so 3x is less than 3x plus 2. What do? We move all the variables to the left no matter what. That's a positive 3x on the right, so we're going to subtract it. And when you do this, something weird happens. 3x minus 3x is nothing. So here's our less than symbol. They cancel on the right like you wanted to, but they also cancel on the left. They don't just make x. They do not just make an x. They don't do this. That would be wrong. Because if 3x minus 3x cancels on the right, it cancels on the left. It's 0 x's. Well, since there's nothing on the left, we have to write 0. The only thing left on the right side, sorry for the confusion with that saying, is the 2. Pardon my cough. So this is weird. The variables are gone. The variables have disappeared, but this isn't the first time we've seen that in this course. When your variables disappeared with equations, that meant we had to make a true or a false statement. So before we would get something like 5 equals 5 and we'd say true, or we'd get something like 5 equals 9 and we'd say false. Well, this is a little more open-ended because of the direction. 0 less than 2, but it doesn't matter that it's more open-ended, it's still true. 2 is bigger than 0, or 0 is less than 2. And back in that previous section, we said true statements meant that there were infinitely many solutions. It means that all real numbers are solutions. So you can say all real numbers, or you can write that double back R. That's kind of the inequality form of that. The graph would be just shading the entire number line, forever left and right. That would be the graph. And then the interval notation is negative infinity to infinity. So all of those are potential answers, but you are generally going to be going after the interval notation. So that one is probably the most important out of all of them. True statements means everything is a solution. So on a number line, you shade the whole number line. All right. So that weird case is going to be very similar to this weird case, but you're going to notice that all I do is change the direction of the inequality. So 3x plus 2, same left and right side, but they change the less than to a greater than. So we're going to subtract 3x on both sides. No surprise there. When you do that, you'll get 0 on the left. You'll get 2 on the right. No surprise there, but now instead it says 0 is bigger than 2. 0 is not bigger than 2. That's a lie. That is a big, fat, false statement. So back in equations, when we ended up with something like 5 equals 7, when the variables disappeared, we said that false is the opposite of true. If true is everything, false is nothing. So there is no solution to this one. So if you were to graph this on a number line, you wouldn't shade anything. So this is me graphing a number line. I'll even put a couple numbers up here just for emphasis. I don't shade a single one. And then the interval notation, there isn't really interval notation. Some people will say you just do the circle with a line through it. That's the empty set. That's kind of the symbol for nothing. Some people might do 2 curly brackets that are completely empty. It's just a bunch of different ways you can answer it. In my math lab, only one of those is an option. So you pick the one that looks like what you have from your notes. But I don't want to give you just the options that are in my math lab, because when you go into calculus, maybe you're not using my math lab. So this C and D, these are very weird examples that show even with inequalities, you can get everything or nothing as a solution. All right, so with that being said, let's move on to the next type of problem, absolute value inequalities. Now, these are split into 2 different cases, case 1, case 2. So this is another case of, sorry for the pun there, this is another situation of you've got to practice this, you've got to learn your cases. It's really nice to understand why the cases are broken down in this way, which we'll kind of talk about. But before we get to that, let's just go ahead and get the grand details out of the way. So the 2 primary cases for absolute value inequalities. You're going to have the absolute value of something. So when I say something, I might mean like a 2x minus 1, or just an x, or x plus 7, anything like that. And then less than a number, or it could be greater than a number. Now, it could have had the or equals as well. That does not change whether you're under case 1 or case 2. So with or without the equals, it's fine. So case 1, if you have the absolute value of something is less than a number, you turn it into this is known as a compound. I said we'd get to it sooner than later. This is a compound inequality where we have the variable stuff in the middle, and then there's numbers surrounding it on the outside. So what is this saying? It says that that's something you have is between, that's what this is saying, it's between 2 values. It's between the positive of the number that was originally here, and it's between the negative of the number that was originally there. So that is very much related to when we had an absolute value equal to a number, where we set the inside equal to the number and we set the inside equal to the negative of the number. That's exactly what's happening. Here's the positive version, here's the negative version. But what we do is, for reasons that will make sense once we kind of eyeball these and see solutions and can talk about it, for reasons, we sandwich the middle stuff between the 2 things. We don't just set them equal because this wasn't an equality, it was a less than. So when the absolute value is less than, we sandwich the middle thing, the something, in between the positive and negative version of the number. Now you might be thinking, okay, Mr. Beckner, how do I know which one goes where? Where's the positive go, the left or the right side? How do I know the negative is the left one? Ignore the middle stuff. You have a negative number, you have less than symbols, and then you have the positive of the number. That's just obvious that the negative should be on the left one and the positive should be on the right one, as long as you're using less thans. Because someone else could come in and say, oh, well, this would be the same thing, right? Do the positive greater than the something, greater than the negative. Yes, that is the same thing. No one writes it that way, so it's a bad idea. Okay. That's the first case. When the absolute value is less than, you make a compound inequality that is drastically different than the second case. And before I even talk about the second case, I want to go ahead and do an example involving the first case, okay? So I know you can see what it says, but I won't talk about it yet. So let's give us some space. Example 1, no. And we're going to solve and put in interval notation. Put in, that's not me repeating a word, that's put in interval notation. I'll even give it the 2 periods so that that is clear. All right, for A, we're going to have the absolute value of 2x plus 3 is less than or equal to 9. Now, in your homework or on a test, you would have to be saying, all right, well, which case is this? Is it the case where I make a compound inequality, or is it the case where I do whatever that says? Well, I've said we're going to go with a case 1, so this is definitely case 1. So, right, this is case 1. This is the absolute value is less than 9. So the way absolute values work, because this needs to be less than 9, you know what, let me not start that conversation until we're done. I don't want to jump the gun. So here's what we do. We take this original inequality and we turn it into the compound inequality. So this number 9 is the thing I'll be changing signs of. I'll need a -9 on the left, and I'll need a +9 on the right. And then in the middle, the something is the 2x plus 3. That's what goes in the middle between the 2 less than symbols. So here's our 2x plus 3. And then you just make sure this makes sense. Imagine this 2x plus 3 wasn't here. -9 is less than +9, so you better be writing less than symbols. But it wasn't just less than, it was less than or equal, so be consistent and give them the or equals. Okie dokie. Now from here, all we do is solve for x. This is the thing we're trying to isolate. The 2 and the 3 have got to go. And the only variation to this idea is whatever you do to one side, you now do to all 3 sides. So to move the +3, we got to subtract 3. Fair warning, don't ever try to move the x out of the middle if I didn't say that yet. Don't ever try to move the x out of the middle. It's a bad idea. -9 minus 3 is -12, less than or equal to, leave the 2x. 9 minus 3 is +6, leave the less than or equal to. Everything looks good, everything looks good. Now we divide all sides by 2, not just 2 sides, all sides. Half of 12 is 6, so that's -6, less than or equal to x. And then 6 divided by 2 is 3. These don't have to be whole numbers, they can still be fractions, decimals, positive, negative, whatever. So here's the answer in inequality form. Now, I did not ask for the graph, but I'm going to do it anyways. Even though I did not ask for the graph, I'm still going to do it. As a teacher, I always do this. If I was doing it on my own, I'll even be honest, I wouldn't, but I've had a little more practice with interval notation than y'all have probably. So the x is between the -6 and the 3, so shade between them. Give it the appropriate symbols, brackets due to the or equals, and there we go. That just makes the interval notation easier to lift. We can see the furthest left and the furthest right. It's -6 and it's 3. We're shading between them. There's no infinities. We got brackets on them. Boom, there it is. That's all it is. So x is any value between -6 and +3. So let's just try, before we go into example B, and I will erase what I'm about to write, because I don't like it left up there permanently. We're good, yes, okay. So let's try a couple of numbers, just for fun. Let's try 0, let's try 3, and let's try 5. In the original inequality and see if it, and I'm talking way up here, we're going to try these 3 numbers and see if they spit out true or false statements. So if we try 0, 2 times 0 is 0, 0 plus 3 is 3. So the left side is 3, and the absolute value of 3 is 3, and 3 is less than 9, so it works. So 0 works, and guess what? 0 is in this correct window. 0 is right here. Not exactly there, but you know what I mean. It's in there somewhere. So 0 worked. Well, let's try out +3, which was that far border. Try +3, 2 times 3 is 6, 6 plus 3 is 9, we add the absolute value of 9, which is 9. 9 is less than or equal to 9, so 9, that works. So this far right solution worked. I didn't say it, but let's also try -6, and I'm going to do that before the 5. So watch this. When you plug in the -6, oh, I gotta rewrite that. 2 times -6 is -12. -12 plus 3 is -9. So we have the absolute value of -9, but when we take that absolute value, it's +9, and it will work. So all 3 of these have worked so far, the 0, the 3, and the -6. All 3 of those numbers have been in this blue shaded region or have been the border. But now let's try 5. Just for kicks, let's try 5. 2 times 5 is going to be 10. 10 plus 3 is 13. The absolute value of 13 is 13, and 13 is not less than 9. So 5 fails. So over here is 5, and it fails. So this solution doesn't end up making sense. So here's the idea. When you have an absolute value being less than a number, when you have an absolute value, it makes the number positive no matter what. So this number, no matter, sorry, I didn't mean to erase, I didn't mean to have the absolute value part. So this piece right here can be as big as 9, or it can be as small as -9, in order for when you take the absolute value to keep it under 9. So this 2x plus 3 itself can be as large as +9 or as small as -9 to make this thing hold true. But if this was a greater than or equal to, it's the exact opposite scenario. If this was greater than, then that means you would need this thing to be bigger than 9 or to be less than -9 to actually make it hold true, which is why this second case, which we'll finally talk about, is the way it is, and that's these 2 lines. So the second case is if you have the absolute value bigger than the number, you create 2 inequalities. So the first case, the absolute value being less than, creates a compound inequality, and your solution is between them. But when you have an absolute value bigger than, you end up doing what's called the tails. It's the outer region. So you have 3 basic regions, the middle, the left, and the right. Absolute value is less than, or the middle. Absolute value is greater than, or the left and right regions. So you still do the positive and the negative of the number, but now it's, you set the inside bigger than the number, and you set the inside less than the negative of the number. So it's because this idea right here, if you try and make it a compound inequality based on the original direction, the positive number, it would have to be like that. And then the negative number, it would have to look like this. But since these don't agree with directions, you can't put it in one thing. You have to basically separate it as this. I've got too much going on now. It's starting to look like a Madden drawing. So basically you have to separate it as to this being its own inequality. So that's the left one, the first. And then you separate it into this one being its own inequality, which would be the second case. And again, the directions have all flip-flopped. All right, rambling aside, background aside, let's see what this looks like. 6x minus 5, that's not a 16, that's an absolute value of 6x minus 5, and then is bigger than 25. So this is clearly case 2. Because we have the absolute value of something bigger than a number. And these absolute values don't already have to be isolated. You might have to do that. Again, I'm just getting down to brass tacks. So in blue, we will make 2 separate inequalities. We can't do the same thing as last time. First, we set the inside bigger than the number. It always basically just looks like we drop the absolute value sign for the first part. So we do 6x minus 5 is bigger than 25. And then we have or, because it could be the other window, you set the inside, do not change that to a plus 5, and you reverse the direction, less than, and you make it a negative 25. So 2 different inequalities to solve. So let's just work on one at a time. Let's add, actually, I will show the arithmetic simultaneously, just so I don't have to keep changing colors. You got to move the 5 over, so add 5 to both sides. You get 6x is bigger than 30 for the first one. And you get 6x is less than, not negative 30, watch your signs, negative 20 for the second one. Then divide by 6, divide by 6, divide by 6, divide by 6. 30 divided by 6 is 5, so that's x has to be bigger than 5. Or x's cancel, leave the less than. Negative 20 divided by 6 is going to reduce to negative 10 over 3. There's the answer in your inequality form. That's the base form. The number line, you are definitely going to want to draw this. Just trust me. Number line. Now put the 5 and the negative 10/3 up here. I'm going to do this wrong for a second. Oh, the 5 I see on the left, the negative 10/3 I see on the right. And this is garbage because 5 should be to the right of negative 10/3 because it's positive versus negative. All right, so let's get it right. Negative 10/3, 5. X is greater than 5 means you're starting at the 5 and you shade to its right. Nothing stopping it, so forever and ever. That's a greater than, so it should be a parentheses. For the other answer, x is less than negative 10/3, we start at the negative 10/3 and we shade left. Nothing stops it, so go forever and ever. And then also a parentheses. See, we've got that separated window of a solution. It's this, then we hop over a section, and then it's this. And again, this idea is going to be seen frequently moving forward. Okay, so interval notation. Because of the two different sets, we're going to need a union joining them. And you need to do them in order. If I do this, I'll pull out red for wrong for a second. If I do this, 5 comma infinity, and then negative infinity, comma negative 10/3. Even though the red ink is accurate, 5 infinity is describing the right one. This one is describing the left one. They're not in order, they're not from left to right, which makes this wrong. So let's get it correct. Negative infinity up to negative 10/3, both with parentheses. Then union, we skip over a bunch of stuff. Sometimes you're even just hopping over the same number, as we'll see in a later example. Not today. And then go from 5 to infinity. That would be our answer. All right, so let's see another one. And now that we've gone over the separated cases, we'll have to determine which one it is and remember. So the final one for this section, 2 absolute value, 4x plus 1 is greater than or equal to 18. Now, some people say, oh, you go ahead and separate the cases. Bad idea. Bad idea, because the absolute value is not isolated. This 2 has got to go. Now, I will admit the 2 isn't technically causing a problem because it's positive. If it was negative, it would be causing a massive problem. So that's something to take account of. I even mentioned that you have to watch out when the original number by itself is negative, but I will admit we won't be doing any of those examples. It's another case of it got trimmed out. All right, so this is 2 times the something with the absolute value, so we got to divide both sides by 2. And that'll give us the absolute value of 4x. I don't need to, I'm just going to go down the page. Absolute value 4x plus 1 is greater than or equal to 9. So we got to ask ourselves, are we under case 1 or 2? And does it really matter which one that you call the number? No, it's just you need to know whether you're making a compound inequality or the separated inequalities. And I'm not saying it's case 1. I was just thinking out loud and writing at the same time. That happens. So we have an absolute value bigger than the 9. So again, I'm not asking you to memorize, oh, it's case 1, oh, it's case 2. I'm asking you to know whether you're supposed to do the 4x plus 1 is less than or equal to 9 and the negative 9 less than or equal on the left. I'm saying, is it this? Or is it the 4x plus 1 is greater than or equal to 9 and the 4x plus 1 is less than or equal to the negative of 9? I'm saying, which scenario is it? When you have the greater than, absolute value greater than, that was the first case that we had written, right? Question mark? I'm doing that intentionally. No, it's not. The first case was the less than, which would have been the compound inequality. This is actually the second case, the greater than. Again, the case number is arbitrary. It's knowing the scenario that you're supposed to get, which is why I just drug you through the coals there. So this is where you make your two inequalities. It's case 2. Case 2. So I'm just going to erase everything below. It's not the left one, it was the right one, but I'm going to rewrite it. So we take the 4x plus 1 is greater than or equal to 9. Again, you basically just drop the absolute value. Or the solution could be the 4x plus 1, don't change that sign, less than or equal to the negative of the 9. And I'm going to show you how I avoid thinking this is a compound inequality afterwards. Couple more lines of work. Nope. That made no sense, right? You saw that happen. That made no sense. Subtract 1 on both sides of both inequalities, and we'll get 4x is greater than or equal to 8, or 4x is less than or equal to negative 10. Divide both sides by 4. Both of these, and we get the x is bigger than or equal to 2, or x is less than or equal to negative 5/2 when you reduce your fraction. Number line. You need your 2 here and your negative 5/2 here. X is bigger than or equal to means shade to the right forever, so arrow, or equal means it gets the bracket. X is less than or equal to negative 5/2 means we shade to the left forever, arrow, has the or equal, so bracket. And the interval notation, there's 2 different regions, so you'll need that union again. The left region is negative infinity up to the negative 5/2. Always parentheses for infinity. It had the or equals, so bracket for the 5/2. 2 to infinity is the other region, in parentheses the infinity, bracket the 2, because consistency. We are. So here's a clue it went wrong. Let's say you tried to do this problem, you got to this point right here, and you said, I'm going to make the compound inequality. But this has a greater than, so you need to stick with that direction. So if you try and do this, 4x plus 1 greater than or equal to 9, there's the right side, but then your left side, you have your negative 9 here. Well, negative 9, if you do this, maybe you just keep them in the same direction. This is a clue it's wrong because you have a negative bigger than a positive. So that's terrible. What some other people might have accidentally instead done, so that's a no, because of the negative being bigger than the positive. The other clue it's wrong is if you go, all right, you do the 4x plus 1 is greater than or equal to 9. And then you go, okay, well, I'm supposed to change the direction. So you do a less than here and then a negative 9. These symbols aren't the same, so that's a no. Okay, well, never mind. Let me just make them all less than. Well, the original symbol was a greater than, so these symbols probably are supposed to be greater thans if you're trying to make a compound. So there's a lot of ways for that second case to tell that it doesn't need to be split up. The interesting thing is the first case, that compound one, you can split it up into 2 inequalities and have it still be true. I'm not going to show that to you though, because I don't want to confuse you. And because it just makes more sense to have it as a compound because the solution is between the 2 regions. All right. So with that being said, that will close out 1.7. Which means we can move on to our final section for the first test, 3.6, polynomial and rational inequalities. So again, this is really like our new 1.8. That's what this is really about. This is what the textbook used to call 1.8, which we feel it should still be 1.8. So we're doing it in that section anyways. There is no 1.8 in the text now, I believe. No, there isn't. This is me flipping through my book just to confirm that idea, just to make sure. We at TCC don't know why they took out 1.8 and moved it to 3.6. It does not fit in there at all for our curriculum. So we're doing it now. So again, in the homework list, you can see it's even in that order. I have alluded to this fact several times. All right, so let's get into it. Now, in the title, we call this Polynomial Inequalities, which means you're going to have these less than and greater thans. That's an inequality. But now we're going to start mixing it with things like x squared and x cubed and x to the fourth. Admittedly, we're only going to do quadratics in this course, which is why I get a little more specific and I say to solve quadratic inequalities. But in reality, these instructions still apply to any polynomial type, just so you know. It doesn't just work for quadratics, it works for cubics, it works for quartics, quintics, and every higher polynomial out there. So what do? You treat it like a problem you were going to factor, like it was an equation you were going to factor. So you move everything to one side, keeping the leading term positive. Now for the polynomial, instead of saying x squared, you would just say the leading term, the highest term, the thing with the x cubed or x fourth, whatever's the biggest number, is an exponent. Then you factor, and I promise you they'll be factorable. You don't want to do these types of problems with a quadratic equation. They exist. They're complicated though. They're much worse. So you'll notice that step 3 looks a little different than just, oh, we'll go straight to setting it bigger than 0 or less than 0. The original inequality sign that the problem gives you doesn't tell you anything initially. So here's this thing with what we call polynomials, when you have something like a factored form x plus 2 times x plus 3. The x plus 2 and the x plus 3, as you go plugging in different numbers, will change signs. And the thing about products, when you're changing signs, is the answers can change signs, like a positive times a positive is a positive times a negative is a negative times a positive is a negative times a negative is a positive. The issue is, as you go through your x values from 2 to 3 to 4 to 5, one of them might change, but the other doesn't. And that can just cause the inequality symbol to inherently not actually flip, but should be flipping to keep everything true or not false. So this is where things get a little different, and we introduce an idea called a test point method. Let's get us lots of space. This is called a test point method. This idea, we will see this again in pre-calc 1 later. You will see it in pre-calc 2 if you're going that way. You will see it in whatever version of calculus you take. And it's not just for inequalities, it's for lots of different things where you don't have just a clear set way to say, oh, well, because it's a greater than, it should be shading to the right, or because it says less than, I should be shading to the left. Because of all this inherent flip-flopping that can happen just because of arithmetic, you have to go and test out points in each of the regions. Now, if one point in a region works, all points in a region work. That's the nice thing. So if your answer was, say, and I'm keeping this simpler, 0 is less than x is less than 10. So 0 and 10 are the splitting points. So you'll have a window that's to the left of 0, you'll have a window between 0 and 10, and a window to the right of 10. So between 0 and 10, maybe you try out x equals 1. If it works for x equals 1, it works for x equals 2, it works for x equals 3. It works everywhere between 0 and 10. If it does not work at x equals 1, then it doesn't work at 2, it doesn't work at 3, it doesn't work at 5, it doesn't work at 6. This idea of true or false, it's like a light switch. In one region, if it works at one point, it works at all points. But when you go between regions, when you go, all right, now I'm switching to 11, so I'm to the right of 10, that true or false idea is probably, notice I said probably, going to change. All of the examples that we will be doing, it will change, but don't get too comfortable. Don't assume that you don't have to test all regions. You have to test all regions because there are problems in the real world where they don't change between skipping over an endpoint. All right, rant aside, let's get down to what all this says. Find the endpoints by setting each factor equal to 0 and solving. So we're actually going to take the less than or greater than, and we're going to change it to an equals essentially and solve. But these will not just be two values that are solutions. They may not even be solutions. These are what we call endpoints. These endpoints are where we will have our brackets or parentheses. The test points cannot be the endpoints. So if you find that your endpoints are 0 and 10, those can't be test points. They absolutely cannot be test points. If you make them test points, you're not going to actually conclude anything. It will either work because of the or equals, or it will fail because it doesn't have an or equals. It won't tell you anything about the windows. So you plug in a test point. Now, here's what's interesting. If I had a room of 10,000 students, each of those 10,000 students could pick different test points in each of the three regions, and all still get the same answer, even though they pick 10,000 different numbers in the process. So maybe I use the value of x equals 1 if my windows were 0 to 10 for the endpoints. Maybe you do 2. Maybe a third student does 3. Maybe a fourth student does 5.9. Those are all fine as test points. Now, do you want to use ugly and large and decimal numbers? No, keep it simple. Use 0 when you can. Use whole numbers when you can. Keep the numbers as small as possible when you can. So plug in a test point from each interval into the inequality and see if you get a true or false statement. If it's true, that means all numbers work in that region, which means you shade all numbers in that region. If it's false, it means that number doesn't work, which means all numbers in that region don't work, so you don't shade it. This is a very simple concept, and students just roadblock here and they go, well, if it's true, do I shade or do I not shade? Simple logic. Think about it. If it's true, that means it works. Shade it. Think. Turn those brains on. Let's use them. All right. So let's try this out. Let's get down to brass tacks. Example 1. Solve and put in interval notation. Even though I am going to put the number line up there, I'm not asking for it. A, we're going to have x squared minus 7x plus 10 is bigger than 0. I'm also going to pull up a graphing calculator after we finish maybe the first two examples. Actually, no, immediately after we finish this example, to show you another kind of way of visualizing this whole flip-flopping and the greater than aspect. Okay. So first step, move all terms to one side. Well, I did that already for us just to get down to, once again, brass tacks. But these don't have to be on one side, and you may have to distribute something. You may have like terms to combine. All that's possible. Stay on your toes. Know your algebra. All right, factor. So let's get down to factoring this. Factor pairs of 10 that add to 7. We have 1 and 10 or 2 and 5 as options. 1 plus 10 is 11, so that's out. 2 plus 5 add to 7, so that's in. So we go x2, x5, greater than 0. But then we got to give these signs to make sure they add to a negative. They'll both need to be negatives. Again, your factoring skills have got to be up to par. In theory, if I was a mean pre-calc teacher, I wouldn't even have to talk that through. I would just go straight to the factored form. I had that pre-calc teacher in high school. I'm a little nicer than that teacher. All right, so now what do we do? Oh, well, we said x minus 2 greater than 0 and x minus 5 greater than 0, right? No. This is where we find what we call endpoints, not necessarily the solution, endpoints, by just setting the factor equal to 0. Even though this says greater than, we're going to just change it a little, and we're going to set them equal to 0. Add 2, add 5, not going to show that work. You get x equals 2 and x equals 5. And if you do this, I'm going to pull out the red for wrong. If you do this, it's wrong, it's wrong, it's wrong. First of all, spoilers, the 2 and the 5 aren't even solutions to the problem. They are just endpoints where we go from on to off. So it's not that the solutions are 2 and 5. If this originally said equals 0, it would be, but no, this was an inequality, and this is where people make their mistakes. These are what we call endpoints. These are endpoints. These are the barriers where I think goes from on to off, usually, where we go from shading to not shading. So here's what I like to do. I like to draw up a number line. Am I going to have enough room? Yeah, I'll have enough room. I can make it work. Draw up a number line, and I'm going to put the 2 and the 5 up there in appropriate orders. And then we have 3 different regions. So our solution could be to the left of 2, or it could be in between the 2 and the 5, or it could be to the right of the 5, or it could be a combination of those. It could be all 3. It could be 2 of those 3. Usually what it is it's usually either the middle or it's the ends, kind of like when we saw with those absolute value inequalities. Absolute values in quadratics share a lot in common. So how do we figure out where to shade? That's where those test points come in. Plug in a test point from each interval. Oh, well, Mr. Beckner didn't tell me what number to plug in. Mr. Beckner doesn't need to tell you what number to plug in. You literally have a million options. So the test points are just numbers. We need a number to the left of the 2. I like to use 0 whenever I can plug it in, and I even like to label my test points, so I'm going to plug in a 0. Between 2 and 5, I like whole numbers, either 3 or 4. I usually pick the smaller one, so 3. And to the right of 5, I could use 7. I could use a million. I could use 9.7. I could use 5.0001. But I like to use the smallest whole number possible. That's just my preference, so I use 6. Go with whatever you like. So I'm going to plug my test points. I'll show the work over here. So for the 0, you can plug it into either this version, which is not factored, or you can plug it into this version, which is factored. It's up to you. I will do it the first one for this problem, but moving forward, I won't do that anymore because I'm going to give you a trick to make your work go quicker. So for the 0, we go 0 squared minus 7 times 0 plus 10. We're asking, is that bigger than 0? Well, the whole left side is just 10 when you do your arithmetic, and 10 is bigger than 0. So we write true. If it's true, we shade that region that that point was included in. So the 0, we're not just going to shade to the left of 0. This is wrong. I don't have my red on, but this is wrong. This is wrong. Just shading to the left of 0 is wrong, because that's the test point. It's that black number I have up here, 2, that was the endpoint. So we shade up to the 2, and we'll put an arrow going left forever. Now, I'm not going to put parentheses or bracket yet because you could end up shading the whole thing potentially. It's rare, and in fact, in this course, you won't see it, even though you should. I hate when they trim homework problems out, but that's okay. All right, so now let's try out the x equals 3. So we get 3 squared minus 7 times 3 plus 10. We're saying, is that bigger than 0? 3 squared is 9. 7 times 3 is 21. So that's 9 minus 21 plus 10. Is that bigger than 0? There's a little dot there. Just ignore that. The equals is above it. 9 minus 21 is going to be negative 12. Negative 12 plus 10 is negative 2. Negative 2 is not bigger than 0. It's false. So if you do this, you're wrong. You are not shading the region with 3. The 2 fails. I'm sorry, the 3 fails, which means 3.1 fails. It means 4 fails. It means 2.1 fails. Try and plug in any of these infinitely many numbers between 2 and 5, and it fails. So don't shade that region. For the 5, I'm sorry, 6, excuse me, 6. I was looking at the 5, that's on me. We'll get 6 squared minus 7 times 6 plus 10. Is that bigger than 0? 6 squared is 36. 7 times 6 is 42. 36 minus 42 is negative 6. Negative 6 plus 10 is going to be a positive 4. So we get 4 is bigger than 0, which is true. So we do shade the region with the 6 in it. So we shade to the right of 6, correct? No. We shade to the right of 5. 5 was the barrier. 5 was the endpoint. Some people even exaggeratedly draw that barrier so they know not to cross it under normal circumstances. Now we can put the parentheses or brackets. So this original problem had greater than, which means there's no or equal, which means these get parentheses. So there is the solution as a graph. But we were supposed to do the solution in interval notation. In fact, I didn't even ask for this, but trust me, you want to do that. All right, that's two separate regions, which means we'll need that union. So we'll have our negative infinity up to the 2, both parenthesed, and then we'll have 5 up to infinity, both parenthesed, with parentheses. Parenthesed sounds weird. Words are weird, though. So I knew that was about to happen. I knew I'm sorry if you can't hear me. Remember, if my audio is ever unstable, if you're watching me live, you can always go back and watch the recording. I'm 99% certain that recording audio stabilization is not an issue because the recording, I record to the hard drive, which I'm smart for doing that because I've heard that people that don't record to the hard drive do have audio issues in post. So, sorry if I'm a little bit kind of, and that was me pretending there. So here's where people go, wait a minute, this was a greater than, and this I shaded to the left on this one. Why on earth did we shade left if this was a greater than? So absolute values and quadratics share a lot of features in that the graph of a quadratic, I'm sure you've seen this before, has this kind of feature. So if your graph looks like this, let's say this is the 0 line. You're above 0 here and here, which means you're not above 0 in this middle region. That's the idea that's going on here. So the direction of this thing doesn't actually tell us anything about whether we should shade left or right on any of these numbers. We don't shade to the right on the 5 and the right on the 2. In fact, if I shaded to the right of the 2, I wouldn't need a union because shading to the right of 2 would also include shading to the right of 5. So let's pull out our, come on, let me please show my desktop. I strongly dislike when that happens. Okay. It's this thing, that's what's doing it. There we go. So on a TI-83, there's a graphing feature if you have y equals x squared minus 7x plus 10. So what we're going to do is we're going to graph this. And here's the picture of a parabola. Again, this is something I hope you have seen at least once in your life. You probably shouldn't be in pre-calc if you haven't. So we're looking for where this right here, we want to know where this thing is positive, where it's bigger than 0. So when you're thinking about this on a two-dimensional graph, you're talking about the height. So the height should be above 0. So here, the x-axis represents a height of 0. So when we look at this picture, wherever we see the graph above that horizontal line, which I can't actually, yes I can. There we go. So this right here is part of the solution because that's where the graph is above the x-axis. And then this right here is also part of the solution. Those are the values. Those particular x values put you at a height above 0, which means they're part of the solution. But down here, the bubble below it, because that's below, that means the outputs are negative, which negatives are not positive, which is why we have to skip that region. And if you look really carefully, if I were to zoom in, you can see this number right here is 2. You hit trace, you can see that's 2. And the other number is at 5. So it's between 2 and 5 where it dips below, so we know that that's not the solution. So now you're thinking, Mr. Beckner, well, why don't I just let the the TI-83 do everything for me? Why don't I just graph that and see, oh, well, there's the numbers. Well, these numbers don't have to be whole numbers. It might be a little tough for you to figure out. Also, calculators aren't supposed to be doing your job. And remember that this is a no calculator test. I'm just using the calculator to kind of affirm ideas here. I'm not using it and saying this is how you're supposed to be doing it. Everything I just did, you should not be doing on a test. If you pull out a graphing calculator on a test, if I suspect that, we're going to have problems. This is a no calculator test. This is a no notes test. And when I go, okay, well, they got the answer right, and when I just randomly pick a student to check out their work and I find that you have no work on x squared minus 7x plus 10 is greater than 0, I am going to suspect that you used a calculator, and I'm going to remove your points for that problem. I reserve that right. Now you might have a nasty email and say, oh, Mr. Beckner, I did it. And then I'll go, well, you didn't show your work, so no work, no credit. Every single problem on a test, if you don't show work, I reserve the right to take away the entire set of points for it. Now that's not something I'm going to do if it's a simple problem. If you get an equation like x plus 3 equals 5 and you didn't show your work for that, I'm not going to dock you. I'm talking about problems that have multiple steps, logic and reasoning to them. I don't think a lot of students can do this problem without showing at least some work. Maybe you don't show the graph. Maybe you don't show the test point stuff because you're really good with arithmetic in your head. I don't know, but you're going to need to show something at some point for this problem. Work is critical. You are supposed to be treating these tests like it's a paper pencil test that you're submitting, and I will look for every layer of work, every layer of detail in your work. All right, let's do another. B. And let's change up the appearance just a little on the polynomial. 3x squared minus 5x is less than or equal to 0. Now, the first thing some of you might be saying is, oh, well, the x squared term has a 3 in front of it, so I got to use the AC method. And you go with that, or maybe you do trial and error. And that's a terrible idea because this is not a trinomial. This is a binomial. There's just two terms. Two terms, you don't do those methods of trinomials. Okay, well you go, all right, well there's two terms, so maybe it's a difference of squares or some a difference of cubes. And if you tried either of those, it would definitely be a no. It's obviously not cubes because the largest exponent's a 2. And it's obviously not a difference of squares because you're going to have a very hard time coming up with something that when you square it gives you this. And you're going to have an extremely difficult time trying to find something that when you square it is this. The x in particular makes it impossible. It has to be like x squared minus 9 or 9x squared minus 25. Those are difference of squares. This is just as simple as a GCF. The GCF of x. It's a very simple factoring problem, but it's sometimes those simple ones that throw people off. So you get x times 3x minus 5 is less than or equal to 0. That's an ugly looking less than or equals. Let me just make it prettier. There we go. Once it's factored, you don't set each of them less than or blah, blah, blah. You set them equal to 0. You actually change. So we're changing this to x equals 0 and 3x minus 5 equals 0. The first one's solved, x equals 0. The second one, you're going to add 5 to both sides to get 3x equals 5. Then you're going to divide 3 on both sides, which will give you x is equal to 5/3. So those are our end points. Those are our endpoints. They are not solutions. They may be part of a solution. They weren't last time. See, the 5 was not a solution. The 2 was not a solution. It went right up to them, but didn't include them. So now what we got to do is probably a good idea to draw the number line. It helps a lot of people. Put the 0 and the 5/3 in appropriate locations. 0 to the left, 5/3 to the right. And then let's do test points. To the left of 0, I'd go with -1 personally. That's me. Between 0 and positive 5/3, which 5/3 is between 1 and 2, I would go with 1 as my test point. It's the only whole number as an option. To the right of 5/3, the smallest whole number is 2. Maybe you're not trusting that that's in the correct region. Maybe you go bigger, like 10. It's up to you. So for our test points, I wanted to do this. Oops. So for our test points, the first one we're going to try out is x equals -1. Now last time we plugged it in directly and we saw what we got. And I said you could have plugged in the factored form or the original form. I'm going to use the factored form this time, the x times the 3x minus 5. And I'm not even going to show all of the arithmetic. I'm going to use a trick. So we're plugging into the factored form. So we get -1 times 3 times -1 minus 5. And we're asking, is this less than or equal to 0? What I'm going to break this down into is just a product of positives and negatives. So the product is the -1 times the 3 times -1 minus 5. So in fact, I'm going to wrap the -1 in parentheses because of that. I keep drawing them a little too big though. It's that issue of I can't see where I'm writing. Okay. So what I'm going to do is I'm just going to write each of these as positives or negatives ultimately. So -1 as in terms of the factor, that's a negative. -1 is a negative. 3 times -1, well, that's -3. -3 minus 5 is -8. I don't care that it's -8 though. I only care that it's negative. And then I'm asking if this is less than or equal to 0. So these, I'm not drawing fractions, I'm drawing negatives. -1 was the first negative. When I simplified this 3 times -1 minus 5, which was -8, I just wrote a negative symbol. Now technically what I have here is -1 times -8, which would be +8. And you can make your conclusion that way. But all we're worried about with factored products is their signs. A negative times a negative is a positive. Are positives less than or equal to 0? No, that's false. The same conclusion as when I had an 8. 8 is not less than 0, so it was false. This right here saves you a lot of arithmetic steps if you've got a whole bunch of these on your plate. We could have done that in the previous problem with A. I could have plugged in the 0 here. 0 minus 2 is going to be negative. 0 minus 5 is negative. A negative times a negative is a positive. Positives are positive, so it would be true, and you'd still shade it. When you plug in the 3, 3 minus 2 is 1, which is positive. 3 minus 5 is -2, which is negative. Positive times a negative is a negative, which is not bigger than 0, so we would not shade that middle region. It just saves you some arithmetic work. If you don't like it this way, don't do it this way. I've showed you both. Use either or. I do not care. So it's false, so we don't shade it. So now we're going to try the 1. So that's going to be +1, and that's the first factor, so product, times 3 times 1 minus 5, that's the second one. Is this less than or equal to 0? 1 is positive. 3 times 1 is 3. 3 minus 5 is -2, which is negative. Notice I didn't say 3 is positive and that 5 is negative. It's the sign is just the whole factor. Again, if you don't like this, don't do it, but it's a good idea. Positive times a negative is a negative, which negatives are less than 0. So that's true, which means we shade the region where the 1 is. 1 is between the 0 and the 5/3. So now let's try out the 2. That'll be 2, that's the first one, times 3 times 2 minus 5. Is that less than or equal to 0? Well, 2 is positive. 3 times 2 is 6. 6 minus 5 is positive. Positive times positive is a positive. Positives are not less than 0, though, so that's false. So we do not shade the region to the right of 5/3. So we just shaded the middle region. Now we got to give them brackets or parentheses as necessary. The original problem had the or equal, which means brackets. But the actual answer is in interval notation. We have our 0, comma, we have our 5/3. We bracket both of them, and that's the answer. So again, when I plugged in the -1, the +1, and the 2, I could have plugged them into the black ink, the 3x² minus the 5x. The conclusion should be the same. I could have plugged them into the factored form and actually shown all the work. The 3 times the 1 minus 5, that was -2. -2 times 1 is -2. So -2 is less than 0, true. Yep, same conclusion. 3 times 2 is 6, 6 minus 5 is 1, 1 times 2 is 2, 2 is not less than 0, false, same conclusion. So far, what we have done is 3.6, part 1. However, so I want you to go ahead and start working on that homework after you finish 1.7. However, since I don't believe these sections should have been split up, that it really should have just been one homework assignment, I'm going to give both of them the same due date. So both of them will have the same due date, which will be a week after Wednesday's class, which is what, the 6th, the 7th, I think the 7th. Yes, the 7th. So anticipate 3.6's homework to be due October 6th. But again, I have given you the techniques to go ahead and complete part 1 if you would like to. These 3.6, these sections are very short. It's like, I want to say 5 or 6 problems with part 1 and like 4 for part 2. So that's kind of nice. You might go, it's probably because they're a little longer problems, and you're probably right. But this lengthy type of problem is going to be a theme in this course. So buckle in, adapt, and learn. So I don't want to start the next section. I'm not even going to go into the instructions at all. We'll see it next time. There's going to be some similarities, but there'll be some differences. So on that note, everyone have a good day. I'll have this uploaded by this afternoon. And, email me if you have any questions. All right, take care, everybody.